First of all, did everyone understand the geometry here? Here we have 3 planets, each has the same mass m/3, and they are at the vertices of an equilateral triangle. Okay? So what is the motion? Motion is that all 3 are actually rotating around the center of mass. So if you look at this triangle, the triangle itself is rotating around the center of mass. And the question asks, what should be the rotation period of this system so that you actually get a stable, well, an equilibrium orbit. Right? Now, what do we need to do? As in any mechanics problem, we need to investigate each body individually and look at the forces acting on it. Let me try to draw this triangle a little bit bigger. So, first of all, what is the center of rotation of this triangle? It's going to be the center of my triangle, right? This is an equilateral triangle. So let's do some geometry. I would like to find out what's the radius of rotation for each one of these planets, because I am given not the radius, but this is given as d, right? So the first thing to figure out is what's the radius of rotation. So what's the angle here? Well, the full angle is pi/3, which means the angle here is pi/6, right? So can I say that this is a right triangle here? R cosine pi/6 is d/2. Cosine pi/6 is square root of 3/2, right? So R is apparently 1/square root of 3 times d. Okay? Good. So how about the velocity of each one of the planets? So this velocity must be perpendicular to the r so that everyone actually rotates around the circle. I'm really terrible. Well, it came out better than I expected. So does everyone understand the sense of rotation, the geometry? Now that we understand which way this planet moves, let me ask you, does it have an acceleration? Yes, it does have an acceleration. Which way is this acceleration pointing? This is uniform circular motion, which means it must be pointing towards the center. So this is going to be my acceleration, and my acceleration magnitude will be v square over r, right? How about the forces acting on this planet? What are the forces? Let's show them with green. What are the forces acting on this planet? Well, there are 2 other bodies in the system. Both of them apply a gravitational attraction force on my planet. So here will be a gravitational attraction force, and here will be a gravitational attraction force between these 2 bodies. What was our rule for the gravitational attraction? It acted on the line connecting the 2 masses, right? So, what is the net force acting on this mass? The net force is a combination of these 2 vectors. It's a vector addition of these 2 vectors. So what do I need to do? I actually need to take the components. So this is going to be Fg times cosine pi/6. So apparently the magnitude F net is going to be Fg times cosine pi/6. But I have 2 such components. So it's going to be twice that. How about the other 2 components? They cancel each other, right? So here's what I have. How about Fg? What's the force between 2 planets here? It's going to be, right, G Each planet has a mass of m over 3 divided by d square. Cosine pi over 6 is square root of 3 over 2. Okay? Good. Then the only thing that's left to write is Newton's equation. F net is equal to m times a. Now I know what F net is. G m square over 9 divided by d square times square root of 3 is m over 3 times. What was a? A is v square over r. So I can write this as v square over. And r is d over square root of 3. Let's try to simplify these a little bit. 1 power of m cancels. 1 power of d cancels. Root 3 here cancels with root 3. So v square is 3 times g m 9 d. So that gives me another 3, which means v is g m divided by 3d square root. Okay? Was that what was asked in the question? No, we're supposed to find the period. So what's the period in this case? The period is going to be the total distance traveled, which will be 2 pi times r, not d, great, divided by v. So it's going to be 2 pi. R was d divided by square root of 3. V was square root of g m over 3d. Square root of 3 is cancelled. So 2 pi d to the 3 halves divided by square root of gm. Sorry? D to the minus 3 over 2? No, I think it's d to the 3 over 2 because d is in the numerator. Am I done? Well, I reached my goal. Certainly. But I would like to check the dimensions. I would like to check the units. What should be the unit of the period here? It should be seconds, right? On the right hand side, 2 pi is unitless. D is meters to the 3 halves. And now I have square root of, what was the unit for Newton's gravitational constant? I don't remember right away, but I know F is g m square over d square. So this must be Newton's meter square, no, divided by kilogram square. So that's a great way to remember the units. And m is kilogram. So great. Let's write Newtons in terms of kilograms, meters, and squares. What's Newton? Meter per second square. So kilograms cancel. This is great. I have square root of second is second. I have m to the 3 halves and m to the 3 halves. They cancel. So this is second. And we actually have, at least the unit wise, this is correct. Does the answer make sense in some limits? It's not easy to find limits here, but what I would expect is that the larger that the system, the larger the planets are separated from each other, the slower this rotation should be. That's sort of correct. It goes with d to the 3 halves. But the dependence on 1 over square root of m and 1 over square root of g, it's not easy for me to see. But nonetheless, I can see nothing wrong with it. So as far as I can see, the limits seem to be right. Now, comes a question. Do you think this ever happens? Do you think you'd have 3 masses orbiting each other? Maybe is a good answer. That's right. That's right. I mean, this is somewhat simplification. All 3 masses need not be equal, though.
When you get a triangle, regular triangle, not regular triangle, but similar regular, like not regular triangle. If you get this, you will probably some probably collapsing.
Okay. Another comment. Why not?
Because planets are created near suns, and if there is sun, it will be bigger.
How about three stars? Do you think there can be 3 stars orbiting around the same center of mass? Like this? Yes?
There is something like that, but it's not solving by Newton's equation, but it solves with general
Relativity. Not quite. Okay, so the answer is, first of all, if you have such a configuration, if you have just 3 very equivalent masses trying to orbit through the common center of mass, we found an equilibrium solution. But it's not a stable equilibrium. If I perturbed one of the masses a little bit, if I just give them what will happen is that mass will fly out, the other 2 masses would start rotating around each other, the other one would start orbiting them. So for 3 particles, it's actually possible to have some stable orbits, but in general, it's not going to be in this configuration. So this configuration is equilibrium, but it's not stable equilibrium. Okay? For example, if I have a pen sitting on its top edge, that's not stable equilibrium. If I wait a little bit, any small oscillation will make it fall down. But if I'm actually holding a pen downward like this is stable equilibrium. If I perturb the system, if I give small velocity to the system, it comes back to its equilibrium point. So that's a big distinction between these two. Okay. Here is one more thing. This 3-body problem of Newton's masses interacting with each other, it's not exactly solvable. Okay. So what does that mean? It means we do not get a general formula for the orbits. What we need is, we know Newton's equations, but that doesn't mean that we can analytically solve, we can express trajectories in terms of known functions. We can numerically calculate, and then we can ask even more interesting questions. For example, is that system stable in the long run? Is the solar system stable in the long run? Is there any guarantee that at some point Earth will not be flung out to outer space? It's been rotating around the sun for 5 billion years, but maybe in the future it will just get off. Maybe Jupiter will pass very close. So these are very hard questions. They are investigated by a separate branch of mathematical physics called chaos theory. So that's also quite interesting. There was a comment, yes. Okay, so that's great. What you can do is you can actually put 5 masses onto a pentagon and calculate the same thing. You'll find another number. It will go a little bit more slowly. But again, this configuration is not very stable. However, what's the limit when n goes to infinity? What happens if I put many small masses onto a ring? It turns out if you put a central mass, that's like the rings of Saturn. That's stable. Then you can actually calculate what should be the rotation of Saturn's ring so that they stay in equilibrium. Yes, for a while.
You said that if you put 3 planets and give force to one of them.
Small forces.
Small force. one of them will rotate around two, and two will rotate relative to each other. Why do not they collapse? For example.
Okay, that's another possibility. That's one of the other possibilities. They can actually. I was just talking about the simulation when these are point particles, so there is no possibility of
For
collapse.
example, about between Earth and Moon, there is gravitation force.
Yes.
So in the universe, there is no friction. If you take F equal ma, there should be acceleration, and two of them should be moving towards each other.
Not quite, right? I mean, they are rotating, so there is a force, there is a gravitational force, but that's giving me the moon acceleration. So moon is falling towards Earth, but also it's moving. So Earth's curvature takes care of this, right? That's what we talked about when we talked about orbital motion. When you have actually enough velocity, you can go around an orbit, and there is still gravitational force which supplies the necessary acceleration to go around a circular orbit or an elliptical orbit.
You mean Earth is making Moon rotate?
Exactly.
Like a robot?
Well, yeah, or I'm saying moon is generally stable because it's actually going with the correct velocity for a stable orbit. Okay?
If it's not rotating, for example, no any sound, for just Earth and Moon, will they move towards each other?
No, I'm not talking about the motion around the sun. I'm talking about moon's rotation around the Earth. Okay? Any other questions? So, this is a lot of fun, and you can you'll see probably, there are a lot of physicists in this class. Gravity gets more exciting, and we have not looked at elliptical orbits, right? So that's more general solutions of motion under this Newton's gravitational law of attraction. You can look at elliptical orbits. You can look at even more interesting systems. For example, the moon is applying a force on Earth, but it's applying this force not exactly to the center. It's actually applying to each bit and piece of Earth, right? If the Earth was totally solid, that's not a big problem. But there is a lot of liquid on Earth's surface, all the seas, right, all the oceans. So what happens that moon's pull creates a deformation in Earth's oceans, and we call this deformation the tides, right? And that actually deformation, because Earth is also turning, that deformation moves through the Earth. So you have the high tide and low tide, and that's due to moon's attraction on Earth. And that was another big revelation. Someone figured out that, hey, Newton's gravitational force not only explains the moon's orbit, it also explains tides on Earth. And here's another interesting thing. If you have two bodies that are rotating with respect to each other, if there are tides on one body, the smaller body is tidally locked. What does that mean? It always shows the same face towards the bigger body. That's what the moon does. Moon's rotation around the Earth and its rotation around its own axis are actually fixed. So we always see the same side of the moon. And the reason for that is, even if the moon started out with a different rotation velocity, it will have slowed down. It will start to show its face towards the Earth because of these tides, because these tides actually dissipate some energy. Okay. All these fascinating things you're going to study if you take an analytical mechanics course. So I think that's enough advertisement for that course. Let's move on. Let's talk about different things. Let's talk about work and kinetic energy. Now, let's see. I'll actually do a very simple calculation. I'll say, hey, let me take a mass m with velocity vi, and let me apply it a constant force. And the question is, what's the final velocity of this object if it has moved a distance d? So this is an extremely simple problem. Let's solve it. If I have a constant force F acting on M, this is going to give me an A. The A will be F divided by M. So how much time would it take to cover this D? We have to find out. But maybe I can do it in another way. I can say that Vf is Vi plus AT. Or in other words, I can find T to be V final minus V initial divided by F over M. So from here, D is going to be what? It's going to be V initial times T plus 1/2 A T squared, right? Well, okay. Let me just put in all the numbers. I'll have Vi times Vf minus Vi divided by F over M plus 1/2. Now A was F over M and T squared is Vf minus Vi squared divided by F over M squared. 1 power of F over M cancels. So here is what I have. F over M times D is Vi times Vf minus Vi plus 1/2 Vf minus Vi, let me do it like that, squared. All right? And I'll write it as follows. F times D is M times, I can take Vf minus Vi out as a common factor. I have Vi plus 1/2 Vf minus 1/2 Vi. Or in other words, I can write this as F times D is M Vf minus Vi. Just a moment. Vi plus Vf. So this is going to be 1/2 M Vf square minus Vi square. So I'll write it in a different. That was a question. Yes.
B plus,
Which one?
when you first derived FD.
Here?
No, one below.
One below. Let's see. I'm taking Vf minus Vi out. So I have Vi plus 1/2 Vf minus Vi, which is, I think it's correct. Come and ask me after the at the break. So here's the thing. This is a very simple calculation, but I'll jump ahead. I'll define this as a new mechanical concept. I'll call this kinetic energy. So the kinetic energy of any mass moving with velocity v is 1/2 m v square. And here we've actually found something, at least in one dimension. Okay. If I'm moving in one dimension, it seems that the change in my kinetic energy, so my final kinetic energy minus my initial kinetic energy, is apparently force, if I'm applying a constant force, times the distance that force was applied. And I'll actually call this something else. I'll call this work is F times D. And I'll state that the change in kinetic energy is equal to the work done on the object. Now, I have made a lot of assumptions. I've said, hey, let's say that this force is constant throughout. In that case, there is only one calculation. I have already done it. I can always say change in K is equal to work done. But this formula is useful not only in one dimension. It's useful not only for constant forces. We're going to relax both of these assumptions. This is going to turn out to be a very important piece of physical equation, if you want. We're going to call this work energy theorem. Let me define the force. Well, okay, you can say, hey, this is obviously 1D because you've shown a force and you've shown a displacement, and you did not actually use the fact that these are vectors. In that calculation, what would have changed if I had initial velocity like this, but if I apply the force making an angle theta? Will I have to change anything in my calculation? Yes, instead of the force, I know that the vertical component of this force will be cancelled. There will be mg, there will be n, there will be the F vertical. So these will cancel each other because this object is not jumping off the plane. So what I actually need to do is I need to take the x component, or F magnitude cosine theta. But see, I can very quickly change I can change the definition of work. I'll actually change it as follows. I'll say work is not F times D. I'll say it's F dot displacement vector. What was our definition of the dot product? It was the magnitude of these vectors times cosine of the angle between them. So here is the nice thing, that that product immediately takes care of my cosine. Okay, so I can actually say work done on an object is applied force on it dot the distance it actually traveled. Okay. So if with this definition, delta kinetic energy will still be work. But what if the force is not a constant? So let's say at each point during my motion, the force changes. How can I generalize my definition of work? Now, here's the thing. Why are you taking a calculus course? The whole thing that calculus course teaches you to do is, if you can do it something for a constant function, you should be able to do it for any continuous function. How do you do that? By going to differential changes, right? Thinking about very small changes. So this is exactly what I'll do. I'll say, hey, during this evolution, when my mass has moved by a very small distance, delta d, and a force F was acting on it, a moment later, let me be more clear. So this is delta d. So I've moved not too much still. Okay. What would be the small amount of work done? Delta work done in that case, it will be F dot delta d. Right. What would then be the total work done when I actually go a finite distance? It will be the summation of all these differential works done. How did we show such a summation? We do not use the sum sign. Instead, when we are summing over differentials, we use it as an integral. So that's what we are going to do. We are going to define work as, that will be the most general definition, integral of f, and instead of saying dd, that is hard to pronounce, I'll call this dl. So at each point on my trajectory, I will have an integral from the initial point to final point f dot dl. Now, don't be too scared. This is a different kind of integral. This is called a line integral. But it's really not too different from what you have evaluated. You just need to keep in mind that at each moment on the trajectory, at each small distance covered, you need to take that small distance and think about the angle it makes with the force. Okay. Let me do a very simple example and also introduce a new kind of object to our discussions. Let's talk about an ideal spring. Now, the ideal spring is a very nice object. It has some relaxed length, L0. And to extend it by an amount delta x, I need to apply a force, and that force increases as I actually try to extend it more. So it actually increases. The magnitude of this force will be a constant k times the magnitude of delta x. And it actually works even more nicely if I want to compress the spring. By an amount delta x, I again need to apply a force, but this force will now change direction. That force magnitude again obeys the same formula. So in general, for a spring, I can say, if this is the force and this is the stretching of the spring, delta x, if I have positive stretching, then I have the force in one direction. If I'm actually trying to push it in, I have the force in the other direction. So what I'm going to say is that's the force needed to apply. But what is the force? And if the point here is not moving, that's the external force. I'm pushing the spring, which means the spring is pushing me back. Similarly, here, if I'm pulling the spring, which means the spring is pulling me to its original position. So I'll do the following. I'll say the force applied by the spring is just minus k delta x. Minus is showing me that the spring always wants to go into its relaxed length. Okay? If I try to stretch it, it wants to go back. If I try to compress it, it wants to go back again. Yes?
What makes a spring ideal?
That's a good question. If this linear relation held for infinite stretching, that would be the ideal spring. Okay? But if you actually go to the lab, get one of the springs there, obviously if you stretch it beyond some length, it will just die, right? It's just going to snap. And even in my, I couldn't really draw a line here. This is not an ideal spring. I should be more careful. An ideal spring really has a linear relation. Okay? Any non-linearity, any deviation from linearity would change that. Now, let's solve a question. Here is the question. I have a mass tied to an ideal spring on a frictionless surface. It has mass m. And here is my L0. I'm at relaxed length. If I give a velocity v0 initial velocity v0 to my mass, what do we expect it to do? It's going to compress the spring. And at that point, its velocity will be v0. Then it will come back again. Right. So I'm asking, what is the maximum amount of compression? Now, this is going to be a hard problem if you try to solve it using Newton's laws. Why? Because the force the spring actually applies to my mass will change with x. It will also change in time because x is changing with time. So can I use work energy theorem to my advantage? Of course. So here's the thing. What's the initial kinetic energy? 1/2 m v0 square. What's the final kinetic energy? There is no motion, so it's 0. What does that mean? Delta k is k final minus k initial must be equal to minus 1/2 m v0 square. That must be equal to the work done on my spring. On my mass, I'm sorry. Who is doing the mass? Who is doing the work? The only thing that's applying a force is the spring. So let's write that. That's going to be integral F spring dot dl. That was my more general definition. Now let's think. Which way is my object moving? It's moving in the negative x direction. Which way is the spring applying the force? Opposite to that. So what's F dot dl? It's always going to be negative. If I say the distance at any point, okay, so I will put actually my axis 0 to be here and call this the x-axis. So this is going to be from 0 to maximum compression. Let me call this x max. What's the spring's force? It was minus k times x times dx. So minus 1/2 m v0 square is minus, k is a constant, it's the spring constant, right? 0 to x max x dx. The integral is very trivial, it's x squared over 2. So it's going to be minus k x max square over 2 is minus 1/2 m v0 square. Minus is cancelled, factors of 2 cancelled, so x max is apparently m over k square root times v0. So that's the maximum stretching of the spring, maximum compression of the spring. Let's check units very fast. This is the last thing we'll do. What should be the unit of x max? Meters. Square root of kilogram. Aha. What is the unit for spring constant? F is kx minus kx. So this is Newton divided by meter is the unit for k. So I have Newton is kilogram meter per second square divided by meter. Then I have V0, which is meter per second. Kilograms cancel, meters cancel, seconds cancel. I have a meter. So I must probably got the correct result. Okay? I'll see you in 10 minutes.